Chapter 11, that is Input-Output Organization. Before we start, let us understand the need of providing an input-output interface between the CPU and external I/O devices. We know that peripheral devices connected to a computer need special communication paths for transferring information. The purpose of this communication lines or paths is to resolve the differences that exist between the CPU and peripheral devices. The major differences between the CPU and I/O devices are the rate at which the data can be transferred, data codes and formats, and the modes of operation. Now, based on this understanding, let us try to understand one of the very important concepts, that is isolated I/O. Many computers use a common bus to transfer information between memory or I/O and the CPU. To differentiate between a memory transfer and I/O transfer, the control uses separate read and write lines. The CPU specifies whether the address on the address lines is for a memory word or for an interface register by enabling one of the two possible read or write lines. So here we have two options when we want to perform an I/O operation. Either the I/O read or I/O write line can be enabled depending on the type of the I/O operation that is required to be performed. Similarly, in case of a memory transfer operation, the control can choose either the memory read or memory write and enables it to complete the required operation. This type of configuration isolates all I/O interface addresses from the addresses assigned to memory words, and that's why this configuration, this mechanism is known as the isolated I/O. Now let us further see how this isolated I/O mechanism can be implemented for a commercial computer system. In the isolated I/O method, it is needed to have separate input and output instructions to access different interface registers by their addresses. So whenever an input-output instruction is fetched and decoded, the CPU places the address associated with that instruction into the common address bus. At the same time, it enables the I/O read or I/O write control line depending on the type of the required I/O operation. In case of a memory reference instruction, the CPU places a memory address on the address bus after completing the fetch and decode phases for that particular instruction, and then activates the memory read or memory write line, again depending on the type of the needed operation. So here, if we consider this isolated I/O configuration, the obvious advantage is that the memory word addresses are separated from the I/O addresses, and that's why memory word addresses are never affected by interface register address assignment. Another method that can be used for the same purpose is known as the memory mapped I/O. As we have seen in the isolated I/O method, memory and I/O addresses are isolated so that memory address values are not affected by interface registers assignment, since each has its own address space. The other alternative is to use the same address space for both memory and I/O. In this mechanism, only one set of read and write signals is needed because there is no distinction between I/O operations and memory operations. Specifically, we can say there is no distinction between memory word addresses and the addresses to be assigned to interface registers. So with one set of read and write signals and no distinction between memory and I/O addresses, this configuration assumes that an interface register is a part of the memory unit. This mechanism, this configuration is known as the memory mapped I/O mechanism. So in this method, any address can be assigned to an interface register but the address that is assigned to an interface register cannot be used for memory words. Due to this property, the available memory address range becomes limited because the addresses that have already been assigned to some interface registers cannot be used for normal memory words. So, if we try to figure out the advantages of this mechanism, then the very first clear advantage is that in the memory mapped I/O configuration, it is not needed to have separate input-output instructions by the computer. I/O data manipulation can be simply done by using the same instructions which are defined for manipulating the contents of memory words. Interface registers can use any address that is not being used by a memory word. So in this configuration, the computer is allowed to use the same instructions, same memory reference instructions in particular, for either I/O transfer or for memory transfer. So the advantage is that the load and store instructions that most of the computers define for communicating with the memory unit, the same instructions can be used for I/O operations as well. No need to spare opcode combinations for defining I/O instructions. Those combinations can be used to define more memory reference instructions. So that is one of the major advantages of using memory mapped I/O over isolated I/O. The selection of a particular method for I/O communication depends on the specifications of the given computer and the choice of the designer. The next topic is about asynchronous data transfer. We know that to build a computer, many hardware components are needed. Most of the hardware components which are used to design a computer system require a clock pulse for their correct operation. Normally, to provide clock pulses to such components, a common clock pulse generator is used. And the devices which are clock driven get that common clock pulse, and then their operations are synchronized. But if the clock driven components operate at different speeds, they cannot be given the same clock pulse. For example, the CPU and peripheral devices, if we consider these two as the two communicating units or entities, then we have to consider their speeds before we try to synchronize their operations by means of providing a common clock. Actually, it is not possible to provide a common clock pulse to these two communicating units, the CPU and any peripheral device, due to the speed at which they operate. That's why these two units require independent clocks. If the two units use a common clock, they are said to be synchronous. If separate independent clocks are used by the two units, they are said to be asynchronous to each other. To implement asynchronous data transfer, that is the main focus of this topic here. So to implement this asynchronous data transfer between two independent units, it is needed to provide control signals to indicate the time at which data is being transmitted, because here that is the only way to synchronize the operations, as the two units are being operated at different speeds and they have their own clocks. So there are two ways to achieve this. One method is known as Strobe, and this is one of the simplest methods to implement asynchronous data transfer. The other method, which is referred to as handshaking, can be considered as an extension of the first method, the Strobe control mechanism. So we'll see these two methods in detail in this topic. Let us start with the first method, that is Strobe. So a Strobe pulse is a control signal that is provided by one of the communicating units to inform the other unit when the transfer has to occur. The concept of Strobe can be applied to a variety of applications that require the transfer of data between two independent units. So this concept is very general and cannot be restricted to only I/O transfers. We can have a timing diagram to depict the asynchronous transfer between two independent units. The sequence of control during such transfer depends on whether the transfer is initiated by the source or by the destination unit. To implement the Strobe control method of asynchronous data transfer, a single control bus is used to transfer the control signals. The actual data can be transmitted using a data bus. Depending upon the direction of transfer, the Strobe signal can be generated and transmitted by either the source or the destination unit. So there are two possible ways to implement a Strobe control based mechanism depending on the source of the transfer. So let us see the first possibility, in which the transfer of data is initiated by the source unit. Two types of diagrams are shown here. If you look at the first diagram, which is actually the block diagram for the required transfer, then the two units, source unit and the destination unit, are connected by means of two buses. The first bus is the data bus, and this bus is used to place the actual data contents so that it can be transferred to the other unit. The second connecting line is actually the control bus. It carries one control signal called the Strobe. Now here, depending on the initiator of the transfer operation, the direction of the control signal, particularly the Strobe signal, can be defined. As we are considering the source initiated transfer here, the direction of the Strobe control signal is from source to destination. So what happens in this mechanism? Initially, when the source unit wants to send some data to the destination unit, it places that data onto the data bus. After that, it enables the control signal Strobe and transfers that signal to the destination unit to the control bus, through the control bus. So the timing diagram for this process can be given like this. So here, when the destination unit receives the Strobe control signal, it receives the data placed onto the data bus, assuming that the data is valid, and after a predetermined time delay, the source deactivates the Strobe signal. So when the Strobe signal is disabled, the data which is available on the data line does not have any significance and it is considered as invalid data. So here the advantage is that the source is not needed to remove the data from the data bus, because as and when it disables the Strobe control signal, the data which is available on the data bus becomes invalid. The destination initiated Strobe control mechanism can be implemented in a similar way. Here, the direction of the Strobe control signal is changed. As the destination unit wants to initiate the transfer of information, it is required to send the Strobe control signal to the source. So initially, the destination unit enables this Strobe signal and that signal is given to the source unit. When the source unit receives its Strobe control signal, it places the data onto the data bus and then this data is received by the destination unit. Upon receiving the required data, the destination unit disables the strobe, and after that the data available on the data bus becomes invalid. Now let us consider the advantages and disadvantages of this mechanism. The obvious advantage of this mechanism is the simple implementation. Only one control signal is required to be sent by either of the communicating units. But this mechanism has a major limitation also. If the two communicating units are using the strobe control mechanism for asynchronous data transfer, and if the strobe control mechanism is source initiated, then the source does not have any way to know whether the destination unit has actually received the data item that was placed in the data bus. Similarly, in case of destination initiated strobe, the destination unit does not know whether the source has actually placed the data on the data bus upon receiving the strobe signal which has been sent by the destination unit. So how these two problems can be solved? The solution of this problem can be given in the form of handshaking, which is actually the extended version of strobe control mechanism. So handshaking includes a second control signal that provides a reply in the form of an acknowledgement to the unit that initiates the transfer. As here two control signals are used, this mechanism is called two-wire handshaking. Again, in handshaking, if we want to determine the sequence of control signals and their directions, then we have to consider the unit that initiates the transfer in the initial state. So, depending on the initiator of the transfer, two types of handshaking mechanisms can be implemented. So, let us consider the first one, that is source initiated. If you look at the block diagram, the source unit and destination unit are connected by means of data bus and control bus. Here the control bus transfers two types of control signals, data valid and data accepted. If we want to understand the sequence of events, then look at the last diagram. Initially, when the source unit has something to send to the destination unit, it places the data on the data bus. After that, it enables the data valid control signal, the first control signal on the control bus. On the other side, upon receiving the data valid signal, the destination unit starts accepting data from the bus. When the data is completely received by the destination, it enables its control signal called data accepted. When this data accepted signal is received by the source, it assumes that whatever is the data sent through the data bus has already been received by the destination unit, and that's why it disables data valid control signal. As data valid control signal is disabled, the data available on the data bus becomes invalid. After some time, the destination unit disables its control signal data accepted. So now the destination unit is ready for accepting new data. So it can be considered as the initial state. The timing diagram for the same is also given here. If we want to implement the other possible form of handshaking, the destination initiated handshaking, then the sequence of events take place in this manner. Initially, the destination unit has to initiate the transfer. So for that, it generates one control signal called ready to accept data or ready for data. This control signal is placed onto the control bus and is transferred to the source unit. When the source unit receives this control signal, it places its data on the data bus and enables data valid. The destination unit then accepts data from the data bus and disables ready for data as it has already received the required data from the source. After some time, the source also disables data valid. So now the data available on the data bus does not have any significance, as now it is considered as invalid data, and this again puts the system in the initial state. Now let us discuss what are the pros and cons of this handshaking mechanism. If we compare this mechanism to Strobe, then obviously this mechanism provides a higher degree of flexibility and reliability because the other communicating unit also provides acknowledgement replies. It has one more advantage. If one of the communication units is faulty or not able to transfer information or receive information, then the process of data transfer cannot be completed. And to detect this type of error, handshaking is based on one error detection mechanism that is called timeout. So here the communicating unit, whether it is source or the destination, it waits for a particular amount of time to receive the required control signal from the other communicating unit. If the desired control signal is not received within that period, then the unit assumes that the other unit is faulty or is not in the state of receiving or transferring the information. So in that case, the unit generates an alarm to indicate the error condition. To implement this timeout in practical systems, a separate internal clock is used. The next topic is modes of transfer. So far we have seen that the communication is needed between the CPU and the attached peripheral devices. But ultimately, the peripheral devices need to communicate with the memory unit. For example, if we consider some input device, let's say a keyboard, then whatever input data is given by the keyboard, the data should be stored ultimately in some memory words. Obviously, computers use some intermediate processor registers to store that data temporarily, but the final location for storing that incoming input data is some set of memory words. Similarly, if we consider some output device, then the objective of that device is to produce the output data to the user, which is located somewhere in memory. So now the question is how the transfer of information can take place between the memory unit and peripheral devices. So there are three classic methods for implementing this kind of transfer: programmed I/O, interrupt initiated I/O, and direct memory access, which is known as DMA. Let us see the first method, that is programmed I/O. As the name suggests, here the transfer of information between the memory unit and peripheral devices take place under some programmed controlled environment. So here a set of input, output and normal register reference or memory reference instructions are used to constitute the required programs. By executing one or more such instructions, the required transfer can be initiated. Now, as the instructions are always executed by the CPU of the given computer system, Here, to implement the programmed I/O mechanism, the intervention of CPU is must. The CPU also has one more responsibility in case of programmed I/O mechanism. The CPU is required to check whether the attached peripheral devices are ready for communication, and if they are ready, the required instructions are needed to be executed. So here the CPU is responsible for monitoring the status of the attached peripheral devices, and if the devices are found ready, the CPU starts executing the required I/O or normal instructions. Now the question is when the CPU should check the status of the attached peripheral devices. If we do not use any advanced control mechanism, then theoretically the CPU is supposed to check the status of the attached I/O devices continuously. So if we try to implement this concept practically, then the CPU or the processor remains busy without any logic significance. And if the CPU keeps checking the status of the attached I/O devices continuously, obviously it cannot complete its normal execution task and the efficiency of the computer system gets affected. So what is the solution of this problem? Here you can recall the concept of interrupt cycle that you have studied for the basic computer in chapter 5. To deal with the said problem, the CPU can be informed by the peripheral device which is ready for communication and wants to communicate with the memory or other parts of the system. So an interrupt signal is generated by a peripheral device that wants to communicate with the system. So whenever an input-output device is ready for data transfer, it generates an interrupt request to the computer. At that time, the computer, or particularly the CPU, stops its current execution task temporarily, stores the return address, and then branches to a service program to process the I/O transfer. So here the transfer of data takes place again between the CPU and peripheral devices. Some memory reference instructions are needed so that the data can be forwarded to the memory unit at the required memory locations. So here also the intervention of CPU is necessary, but the CPU is not required to check the status of the attached I/O devices unnecessarily. The CPU can be interrupted by the peripheral device which is ready for communication, and that's why some of the clock cycles can be saved during which the CPU can perform its normal execution task. The third possibility of implementing the transfer between peripheral devices and the memory unit is DMA. DMA stands for Direct Memory Access. So here the CPU is not involved in the actual transfer of information, though the CPU is required to initiate the transfer by providing the access of memory and other control buses to the attached peripheral device which is ready for communication. So one DMA controller is needed to practically implement this concept. The interface which resides between the CPU and a peripheral device can transfer data into and out of the memory unit using the memory bus directly. So when the memory bus is granted to the DMA, or specifically the DMA controller, the data can be directly transferred to the memory unit. So the advantage of this method is that the CPU is not involved in the actual transfer of information that takes place between some I/O device and the memory, and that's why during that time the CPU can continue with its program execution task. We'll see the details of DMA in the next lecture. Now let us see an example of programmed I/O mechanism. So if you look at this configuration, two main communicating entities are present here. One is the CPU and some I/O device is considered as the other communicating unit. These two communicating units are connected by means of an I/O interface. The type of the I/O interface depends on the type of the I/O device attached to the computer. To provide communication paths between the given I/O device and the interface, a data bus, which is actually an I/O bus, and a control bus is used. As you can see here, data valid and data accepted signals are communicated between the interface and I/O device. So we can say that a two-way handshaking, a two-wire handshaking mechanism is used here for communication. Interface register is assumed to have some set of data registers and status registers. Here each status register consists of one flag, which is named as F in this diagram. To connect the CPU and the I/O interface, data buses, address buses and control buses are used. Here for simplicity, only one data bus, address bus and control bus is used. So here let us assume the scenario in which the attached I/O device wants to transfer some information to the CPU, which is required to be forwarded to the memory unit. So the I/O device places the data to be given on the I/O bus. The data is first given to the interface. When the I/O device places that data onto the I/O bus, it enables the data valid signal. Upon receiving the data valid and actual data, the interface generates the data accepted control signal to complete the process of two-way handshaking. The data received from I/O device is stored in the data register by the interface. Depending on some control conditions and data received by the data register, some of the bits of the status registers are set or reset. Now the data that is to be forwarded to the CPU is available with the interface. Again, a two-wire handshaking mechanism can be implemented between the CPU and the interface so that the data can be successfully transferred to the CPU. For transferring the data from the data register of the interface to the CPU, the data bus is used. If some address values are required to be provided by the CPU to the interface to complete this transfer, then that address value is placed onto the address bus. For providing the control signal inputs for read or write operation, the CPU uses I/O read or I/O write control values which can be forwarded through a control bus. So here the question is, when the interface transfers the data to the CPU. So when one of the bits of the status register, particularly the flag bit F, is set to 1, at that time the interface initiates the transfer of data to the CPU. So here if we consider the programmed I/O configuration, then the CPU is supposed to check the status of this flag bit F. If it finds that F is set to 1, at that time it initiates the transfer. Now we can consider the same configuration if we want to understand an example of interrupt initiated I/O. Here in programmed I/O configuration, the CPU is supposed to check the value of F continuously. Now if the CPU does not want to waste its clock cycles in simply checking the value of F, then an interrupt can be generated by the interface whenever some new data is received in the data register. At that time the interface can set F to 1 and the generated interrupt can be given to the CPU so that the CPU can receive the signal, control signals which are generated by the interface, as well as the data placed onto the data bus. Now, whatever is the case, whether programmed I/O or interrupt initiated I/O, the question is how the CPU determines the address of the required service routine, because upon receiving the notification, upon receiving the interrupt, the CPU is supposed to branch to a specific I/O service routine. So there are two ways to specify the address of the required I/O routine. The first method is called vectored interrupt. So in case of an vectored interrupt, the I/O device which is interrupting the CPU provides the address of the required I/O routine. It can also provide some additional control information, for example, how the CPU can go to that address. So in general terms, the branch information for the required service routine is provided by the source that interrupts the CPU. This information is provided in the form of an interrupt vector, and that's why this method is called vectored interrupt. So here the CPU is not required to determine any address because the I/O device that interrupts the CPU also provides the required branch information. And the other method, which is referred as non-vectored interrupt, the branch address, the branch information is not provided by the interrupting device. Here, the required service routines are always stored at fixed memory locations. So depending on the type of the attached peripheral device, the CPU determines which of the service routines should be called. So this decision is required to be taken by the CPU in case of the non-vectored interrupt. The next topic is priority interrupt. In commercial computers, many peripheral devices are attached to the computer system, and it is possible that many of them generate interrupt signals to access the CPU or memory unit simultaneously. Now, if the device requests are not conflicting and if the computer is able to serve the request at the same time, then there is no issue. But what if the computer, specifically the CPU, is not able to serve all the incoming interrupt requests, I/O requests at the same time? In that case, the CPU has to choose one or more specific devices that should be served depending on the current condition of the computer system. So the question is how the CPU determines which of the interrupt signals should be served. So for that, the computer assigns priority values to peripheral devices. So whenever a peripheral device generates an interrupt, it also provides the priority value associated with it. These priority values are useful in case of multiple simultaneous interrupt requests. So let us see how these priorities are evaluated, and based on that evaluation, how the CPU takes a decision to serve some of the attached peripheral devices. Two methods are used for this purpose. One software-based method is known as polling method. So here one software-based system is used to establish the priority of simultaneous interrupts. Whenever simultaneous interrupt requests come, the control always jumps to one common branch address. This common branch address is actually the first location of an interrupt handling program. This interrupt handling program is responsible for polling the interrupt sources in sequence. As the devices already contain priority values and these values are provided with the interrupt request, the interrupt handling program considers the highest priority source first and checks whether its interrupt signal is on. If its interrupt signal is found to be on, then this device, the associated peripheral device, gets the access of the required components of the computer. And in that case, the control branches to a service routine for that particular source or IO device. Now, this method is simple to implement if we can implement this interrupt handling program. But the limitation of this method is that if the logic of this interrupt handling program is complicated and time consuming, then sometimes it happens that the time needed to poll all simultaneous interrupt requests exceeds the time that is needed to service the IO device, which is obviously not feasible to implement practically. So what can be the solution to this problem? In that case, we can use one hardware based method that does the same thing. That method is called daisy chaining mechanism. So in the next lecture we'll see how to implement this daisy chaining mechanism using different hardware components so that the limitation of polling method can be overcome.